So let me do this demo for the freeform timed assessment for thermodynamics part 2. I just did part 1, and same with the part 1. I've seen the question before, although I think I'm forgetting now. I did have to look because I've done this demo 3 times already. So if I simply start without preloading the dice, then there's a good chance I will get one of the 3 questions that I've done before. And in fact, I had to re-roll the dice several times before I finally got a question that I haven't done before, and I'm trying to remember what it was. Oh, I think it was about Stirling engine. I haven't done it before, so here now I'll start to the Stirling engine question, but I promise I haven't had a lot of time to think about it. I just rolled the dice before I started this virtual class session. So let me start. And I do like a part 2 better because it's a more substantial, like a physics heat engine portion of the freeform timed assessment. So this PV diagram shows the Stirling engine cycle, very similar to Carnot cycle. The difference is what's adiabatic in Carnot is isochoric. A, B, and C, D are isothermal processes like the Carnot engine, working fluid. Answer the questions below, and any physical constant need to organize and attach. Yeah, I probably will need this figure at some point, so let me just paste it into OneNote. Can I move this now? Okay. Yeah. Okay, that's in OneNote. Answer and explain briefly during which of the processes, I can refer to the figure there, does the heat flow into the system, which does the heat flow out. Yeah, so here the answer will be slightly different from Carnot cycle. So for Carnot cycle, I would have said A B process involves heat flow into the system, and I would have stopped here. No other process involves heat flow into the system, but with the Stirling engine cycle, the isochoric heating involves heat flow. So also D2A isochoric heating process involves heat flow into the system. 2. During which of the processes does heat flow out of the system? Again, C to D, like with the Carnot cycle, involves heat flow, the waste heat flowing out. CD process involves heat flow out of the system. And unlike a Carnot cycle where BC was adiabatic, it's not adiabatic, it's isochoric cooling. So I need to say also BC isochoric cooling process involves heat flow out of the system. 3. During which of the processes is non-zero work done? A to B and C to D. A, B does positive work. C, D does negative work. The isochoric processes do no work. And this is again different from the Carnot cycle where adiabatic process does involve work being done, so that for temperature can change without the heat flow. So B, what is the net work done over one cycle of a Stirling engine cycle? Give your answer in terms of the given quantity. So this is the thing that takes a lot of time. Analyzing heat engines, as you have seen it demonstrated in the homework, you just gotta work through the whole thing. There's no real shortcut. So let me do that. So A to B, this process. So it's an isothermal process. So I can say change of internal energy is 0. That makes some things easy, because that'll mean the first law, which says the change of internal energy is the net heat flow minus the work being done by the gas. So this implies that the heat flow, let me call that QH, is equal to the work done going from A to B. And I think it's this part that I have to calculate. I mean, you could look up the formula in the textbook, but let me just do this calculation. So the work being done by the gas, you start out with the infinitesimal amount of work being done, which will be the pressure times the infinitesimal change of volume. Here pressure is the function of the volume through ideal gas law. PV is equal to NKBT. So using this, I'm going to rewrite pressure as NKBT over V. And actually, I'm going to do one more rewriting because so here T would be actually TH, temperature at the high isotherm. And the one additional substitution I'm going to do is I'm going to use the fact that ideal gas law applies here, meaning PV is equal to NKBTH. This is constant. So I can basically pick any point along this isotherm and treat the product as a constant. Like PA times VA, that will be a constant. I can use that to replace this. So I'll make the substitution and say that this is PA times VA. That way I have a, because I don't think the question gave me any of the like N or KB didn't give me those. It gave me pressures and volumes, which are easily measured, and the temperature. So I'm rewriting it in terms of pressure and volume. So I imagine doing the integral of this from initial A to B, integral of this from A to B. Then what you end up with is, so on the left hand side, that'll be the work being done from A to B. That's equal to right hand side. I'm gonna do a lot of the calculations in my head, PA, VA, I can pull them out. It's 1 over X, so antiderivative that is natural log of V. So I have, let me do this part step by step. Natural log of VB, upper limit, minus the natural log of VA, lower limit. And then I'm going to do logarithm algebra to rewrite this as PAVA times one single natural log of VB divided by VA. I like this form better because then the units cancel out. The argument to natural log is unitless as it's supposed to be. So that's the amount of work being done. And from what we said above, that is also the amount of heat transfer. That's A to B. B to C. Here the simplifying thing is that the work being done from B to C, B to C is equal to 0. So that means we can just say the change of internal energy gives you the heat transfer. It's QH1. I guess I'll call this Q low 2 because it's gonna be one of the waste heats. So yeah, and the change of internal energy, you're going from one isotherm to the other isotherm. So change of internal energy is basically is it monatomic or diatomic gas? Does it tell you? Ideal diatomic gas. So this factor you kind of just have to remember. For diatomic gas, it's the 5 halves and KB delta T. And I'm gonna again use the I'm gonna rewrite NKB as basically let's see, pressure at B, volume at B, divided by temperature at B, which is TH. So with that, this quantity should be 5 halves. So NKB is PB VB over TH times the change of temperature. So that's TH minus TL. Okay, that's a B to C done. And C to D, I think it's going to be the basically same thing. So I'm going to use this formula with the variables correctly substituted for. So work being done from C to D, let me write it in a way that it's manifestly negative, minus pressure and volume at the starting point, PC VC times the natural log of, it would have been final over the initial, that's where actually the minus sign comes from. Pulling out the minus sign, I flip them, so it'll actually be initial over final. So VC over VD. This way the or I guess VC over VD is VB over VA. So let me just make this substitution, VB over VA. So this natural log is now positive. That's what I mean. This is manifestly negative. That way, I don't make any unintentional sign errors. D to C, D to A. It's the kind of reversal of B to C. So actually, is it literally reversal? I'm trying to think through. Yeah, because this NKB, that's a constant. So actually D to A, this will be, so you can say the Q, and by the way, so this is also what WCD, that's also equal to QL1. And here for D to A, we can say the QH2 heat input, that is actually equal to QL2. I wrote that as a positive thing, right? So I can just say that is equal to QL2. These kind of two things just cancel out, the heat transfers. I mean, they don't cancel out for the purpose of the efficiency calculation, but so yeah, okay. So I got 9 minutes. So over one cycle, Stirling engine does net work. That would be so let me finally write out the part A. So with all that work done, part A, I can say net work done is equal to WAB, a positive quantity, and I'll just say plus WCD, which will be a negative quantity. Or writing it out, it's PA VA natural log of VB over VA minus PC VC natural log of VB over VC. It's possible I need to rewrite this. Let's check. Are they one of the symbols I'm allowed to use? Yeah, I'm not allowed to use. So PCVC, I'll have to rewrite that. So the way it'll be rewritten is, so from ideal gas law, PCVC is equal to NKBTL, and I have PAVA, both of which I'm allowed to use, is equal to NKBTH. So I basically solve this for NKB. PAVA over TH, and plug that's the NKB, and plug that into there, which will give me PCVC is equal to PAVA TL over TH. So this will be just the PAVA TL over TH. So now that's in terms of everything. Oh wait, that's not VB over VC, that's a VA. Alright, so I can simplify a little bit, but this is enough where it's all in terms of the variables that I'm allowed to use. PA times VA times natural log of different from log, log based 10, VB over VA, VB over VA, minus. So I could have factored up. Actually, let me factor up PAVA times natural log as I'm doing that. So the first term just becomes 1 minus, and factoring out all those gives me TL over TH in the second term, which I think it makes sense. Yeah. What is the net work done? Yeah, so that's the net work done. What is the efficiency of the Stirling engine? Give your answer in terms of given quantities above. Yeah, it's complicated. Don't do, like if you do this, TH minus TL, the whole thing divided by TH, that will be graded as incorrect. That's the Carnot engine. Stirling engine, it's complicated. So let me do it this way. So I'm gonna have this expression for TH. So work done. So that's the general definition of So general kind of definition of efficiency of any engine, Stirling, reversible, irreversible, is the efficiency is the net work done divided by not net heat, which will be same as net work, but the heat input at the high end. So here I need to express my heat input in terms of both the one along the isothermal. This is what will give you the Carnot efficiency, but I have to add that additional heat input QH2 that I got in the process DA, that I have expression for that here. So for the purpose of evaluation, it doesn't care how complicated my expression looks. So let me do it this way. This is the network. Oops, not here. Here. Oh, that's the network. Divide that whole thing by the heat input. So that'll be the QH, which I have there. P A V A times natural log of VB over VA. That's QH1 plus I need QH2, which is same as QL2, both positive quantities, the way I wrote. And I need to PB, VB, can I use it? Or I can use VB but not PB. So I think a PB, VB over TH, that's meant to be NKB. So I can just write that as PA, VA, I think. That'll be fine. So PA, VA over TH, and then I'm sure I can simplify more, but let me not. I'm under time limit. So yeah, this is the efficiency of the Stirling engine. Now, what is the numerical value of the efficiency if the Stirling engine has a volume expansion factor of that? Okay, all right. So let's plug that into into Wolfram alpha. So Wolfram alpha, PAVA. So I think PAVA, it's in every single term. It'll cancel out. I don't have to. So in fact, I can erase it here, so it doesn't depend on that. Not sure what the system would have done with that. If it would have been graded as incorrect for having those things. Maybe not. I'm not sure. So let me get Wolfram alpha. So I need the natural log of the VBA over VA is 3 times 1 minus the TL is 260 divided by 470 divided by natural log of 3 plus 5 halves times TH 470 minus 260 TL divided by TH 470. So that should give me a numerical thing, a decimal form. Okay, so 0.2215, 0.2215, or 22% efficiency. I think that's right. So let's see. Let's hope I didn't make any mistakes. If I did, I'll show you the answer key. Let me add work. I think I have time to add work. So the work is what I've been kind of scribbling here mostly. This way. Now, just to overlap some portions of the image. I messed up when I wrote that in. So overlap enough so that there's no information getting lost in copy and paste, and also things are not ambiguously wrong. And then I'll paste in this. I guess what I'm considering to be wrong is being ambiguous. You could be ambiguously right technically, but I think if you're ambiguous, then even if you are technically right, you are not spiritually right. All right, let's see. 60%. Does that mean that's getting everything right? Let me check. Some questions, will be graded as incorrect just based like this is 0%. So yeah, I got 1, 2, 3 boxes right out of 5. So I think 60% is getting everything right. But let me go get my instructor access thing to just to confirm that 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 is indeed all the correct answers graded as correct, and that anything that's I didn't get credit for is the manually graded portion that somebody needs to go in and give manual credit for. Great. And one other person has done it so far. Here's test the students thing. Let's see. So, I'm sure this is right. Yeah, A, B, D, A. Yeah, all these. Yeah, all these. And yeah, this is graded as correct. And yeah, that's the exact form. This, I think, could have been simplified more. Could it have been? Oh yeah, that is the exact form that the answer key has. Don't know how it would have graded if I left the PA, VA stuff in. Efficiency, yeah, and this is the detailed solution. This is kind of the old style of me writing these questions. I stopped doing it. Now everything is manually graded. I don't split this solution. I don't do that. Yeah, so for this question, you basically have to work through each part. Kind of, there's no shortcut around having to work through each segment. It's tedious, but my goal is for you to get to a point where this feels tedious, not difficult. Time consuming and tedious, but all easily doable, mechanically doable. That is, I think, the place that's nice for everyone to be at. So yeah, Parsi is So we use network and QIN that I calculated as part of the process. You need that, and so simple as it's gonna be. And plugging all those in, you get this. So yeah, that's this part. I again want you to add this another example of thermodynamics freeform timed assessment demos, and I hope this is useful to people seeing. Thank you.